Hello everybody. In this video we are going to be looking at the solution to Physics 1 Doppler effect due right now, number 2. Let's take a look at our problem. We have a car traveling at 24.6 meters per second, passes by a person standing on the side of the road and blares its horn as it passes by. That's just obnoxious. I'm sorry, that must just scare the heck out of the person standing there on the side of the road. That's just a really rotten thing to do. Oh well, let's see. If the air temperature is 24 degrees Celsius and the car's horn emits a sound at 375 hertz, what is the frequency heard by the observer A as the car approaches? So in this problem, we are given the frequency of the source, which is the horn on the car driven by the obnoxious driver, and that's 24.6 meters per second. It's going to be positive because in this part of the problem, the car is approaching the observer. So the car is moving toward the observer, therefore it has a positive velocity. The frequency of the sound wave is 375 hertz, and we are given the air temperature of 24 degrees. I need to know how fast the sound wave is going to travel in air at 24 degrees Celsius. So before I can determine that, I do have to convert my temperature from Celsius to Kelvin. That should be a pretty simple operation by now. We know in order to convert from Celsius to Kelvin, I take my Celsius temperature, add 273 to it, and that will give me a Kelvin temperature of 297 Kelvin. I can then take that temperature in Kelvin, plug it into my speed of sound in air formula, and when I do that, I'm going to get a velocity for the sound wave of 345.2 meters per second. So now in order to find the frequency of the observer, I'm going to use my Doppler formula, plugging in the frequency of the source, 375 hertz. I know that the velocity of the sound wave at 24 degrees Celsius is going to be 345.2 meters per second. My observer is stationary and the source is moving at positive 24.6 meters per second. And when I do out the math for that formula, I am going to have an observed frequency of 404 hertz. Part B asks, what is the frequency heard by the observer after the car passes? So everything else stays the same as the first part. The source is still moving at 24.6 meters per second, but now it is going to be negative 24.6 meters per second because it is moving away from the stationary observer. So the car, or the source of the sound wave, the car is moving away from the observer, so its velocity is going to be negative. The frequency of the horn is still 375 hertz. My air temperature is still 24 degrees Celsius, which means that the speed of the sound wave is still going to be 345.2 meters per second. Plugging all of that into my Doppler formula, again, the frequency stays the same, the speed of the sound wave stays the same, the observer is still stationary. The only thing that we're changing is the sign on the speed of the source of the sound wave, changing it from positive to negative. And when we do that, we are going to have an observed frequency now of 350 hertz. And note that now that it's moving away, the observed frequency is lower than the source frequency. When it was moving toward the observer and we had an observed frequency of 404 hertz, the observed frequency was higher than the source frequency when the relative motion between the two was toward. And now that the relative motion between the two is away, we hear a lower frequency.